few months ago I made a video showing this. This is the MK14 microcomputer. This is obviously the advert for it that came out when it was first released. It was released back in 1977 by scientists of Cambridge, actually a division of Sinclair Research. It sold it for about £39.95 as a kit. It's equivalent to about £245–250 in today's money. And they sold about 15,000 of them. Unfortunately, I wasn't one of the people to buy one. I couldn't afford them at the time, but I did spend many hours looking at this advert, trying to figure out how I could get one. And here I am over 40 years later, and I finally got one. Unfortunately, I couldn't find one anywhere to buy at a sensible price, but as you may know, I produce reproduction boards for vintage computers, so I decided that this would be one of the projects and I would produce my own boards, so I could build my own MK14, and as you can see I finally have one that is complete and works. I sell these boards on eBay if you're interested, but what I wanted to do in this video is give a very quick introduction to any issues you may get if you do decide to try and build one, and a very quick introduction to how to use it. And we'll be making some more follow-up videos to show in more detail how to program it and connect various things to it. As part of the parts that I supply, I can also supply the overlay for the keys. This was always one of the issues with the MK14, and that the keys were unreliable. They were the sort of rubber bumper type keys, and they had a habit of failing from what I gather, and were very difficult to use, very similar to the ZX80 and 81 type keys, which were always a pain to use. So on the board I designed, the only real change I made to the original was to include the ability to fit actual proper keys, and then these fit underneath and allow you to operate the keys in a much more reliable way. It's far less frustrating to use. The main issues you'll get when you try to build one of these is trying to find a couple of the parts. For the most part, some of the items are easy to get hold of. The main processor is relatively easy to get hold of. Most of the rest of the chips are standard 7.4 series chips. The PROMs are a little bit rare. I'll show later on in this video how to go about programming those. The RAM chips are relatively easy to get hold of. They're specified as P21111As in the parts list, but you can use basically any type is equivalent. In this case I've got AM9111s, which work just as well. The parts list that is in the manual, and if this board, as I say, is a true reproduction, so you can just use the original manual that came out for the MK14 and it will work just fine. The schematic is identical, and as long as you follow the instructions on there, then it will work without any problems. So the 8060 processor you can get fairly easily. The PROMs you can get, and you can find the code for those online. RAM chips, as I say, are fairly easy to get hold of. The in-out device is optional, as are two of the RAM chips, but you will need this if you want to do any significant interfacing to, for example, hook up a cassette or to drive anything. The other devices are for the most part fairly easy to get hold of. The device for IC11 is listed as a DM80L95, but you probably can't find those, but you can just substitute that with a 74LS365 and that will work just fine. The rest of the parts are fairly standard apart from the display, which I'll come back to in a minute. The only other devices you need to be careful of here are the 7408s. You'll notice in the listing, although there are 3 7408s, it lists 2 of them as 7408 and 1 of them as a 74LS08, and there's a very good reason for that. If you try to just put 74LS08s in all three positions, you will more than likely find that the unit either won't work at all, or it will work intermittently, and you may find that you destroy various chips, including PROMs and processors and possibly various other devices on here as well. The reason for that is fairly self-evident when you look at the schematic. So, like most equipment of this type that uses an LED display, the display is actually strobed, so it's only lighting up one digit at a time. So what it does, it feeds the correct signals to each digit, strobes the digit for a short time, moves on to the next digit, and then strobes whichever segments of that digit it wants to illuminate. And it does that rapidly, so it appears as if they're all on at the same time. The way this works is it has two sets of inputs. One is for the segments and one is for the individual digits. Now, because they're both fed from ICs, 74 ICs, there is no current limiting other than the inherent current limiting of the ICs. Now, for a 7408, if you look at the spec sheet, you'll see that there is an inherent current limit. It's only going to be able to provide a few milliamps. Although the spec sheet doesn't make it clear, if you look at the actual spec sheet that shows the internal circuit, you'll see why that is the case. That means that you can hook up LEDs directly to the output of these 7408s and you won't do any harm. However, if you substitute these with 74LS08s, they have a much higher drive capacity, and in fact they will drive the output to as much as 100 milliamps, even though the input is only rated for each device at maybe 20 milliamps. Now, unfortunately, that means that it's very easy to put a huge amount of current through the display segments. Not only will that damage the display, but it will also damage the other chips, and it will cause the chips to behave in a very erratic fashion, which can cause them to load up the address bus. That in turn can cause the PROMs to fail, or even the processor itself to fail if you leave it running for too long. There are two options you have at this point. You can either source 7408s and make sure that you don't use the LS in these two positions. They are tending to get quite expensive and fairly hard to get hold of. So what I've done instead is, on the one I've built, I use 74LS08s. Well, what I've done, I don't know how well this will show up, but in the segment inputs to the display, I've inserted a 150 ohm resistor. Now, you want to put them in the segment lines, not in the digits anodes, because if you put it in the anode rather than the segments, you'll find that the brightness of each digit will vary depending on what's being displayed. What this does is it puts a current limit in the loop between the two devices that are driving the LED. So not only will it protect the LED, but it will also allow you to use 74LS devices here, even though they would normally have a much higher current output. And if you do that, it works just fine, but don't use 74LS08s unless you include the resistors. So in terms of the displays themselves, they are quite hard to get hold of. The easiest thing to do is to find an old calculator that uses the LED bubble type display, take it out, and they will generally work fairly fine. The display type that's specified in the Microcomputer manual is either the 1188 or the 1198, and I tend to use the 88s. They're easy to get hold of, and it's essentially any old 7-digit calculator tended to use one of these two. They're not especially cheap, but normally you can pick one up for about £8 or £10 off eBay. Take the display out and then just solder it into the board as you would normally, making sure that you use the resistors if you're using the 74LS series. The rest of the circuit's very straightforward. It's just a case of soldering the parts in, making sure the supply is as it should be. You don't particularly need this large capacitor if you're using a relatively good supply. I only fitted it because it makes the unit look more authentic. It was only there if you used unregulated or unsmooth raw supply, but because I drive this from a bench supply, then it's not really needed. So we'll have a quick look at how to program the two proms, and then once we've done that, we'll see how to actually operate the computer. There are of course many ways that the binary image file for the proms can be split into the two blocks that are required. What the MK14 needs is the lower 4 bits of each byte to be put into one prom and the upper 4 bits put into the other prom. And what I'm going to show here is the way I go about doing this, but of course it will depend on what programmer you have as to how you go about doing this. But a simple way is to get the programmer to do it itself rather than going through and trying to find a manual route. So what I've got here is the programmer that I'm going to use to do this open already. I will load the binary file that we're going to use. So this is the binary file for the MK14. There are a few different versions, but this will work irrespective of which version you intend to use. So once we've got it open, we can look at what's in that file. Now if you look at this and compare it with the source code or the binary file opened in a hex viewer, you'll notice that this is, or it looks incorrect. And the reason for this is because we have the 74S prom selected, and this particular programmer masks off the upper 4 bits when you select that device. So if I just select a different device, so this is an 8-bit EEPROM. If we now look at the data again, you can see that the lower 4 bits are the same, but we're now seeing the entire byte. And what we need to do is, for each byte, is to create 2 images from each byte. One that contains the lower 4 bits and one that contains the upper 4 bits. And those images can then be programmed into each of the proms. So now we have an 8-bit device selected. What we can do is simply save this to an image where we will only use the lower 4 bits. In other words, because we already mask off the top 4 bits when we select the prom, we can actually leave this file as it is. But just for clarity, what I will do is save the file with a different name. We only need 512 bytes, but because we've got an 8K EEPROM selected, the default buffer size is too big. So what we can do is reduce that to the size that we want. Select where we're going to save the file to, and then this will be the lower prom image, so we'll call it lower. So we've now got a file that is the lower 4 bits. It's actually the identical file to what we started with, but when we open it in the programmer, the upper 4 bits will be masked. What we now need to do is create another image file that consists of just the upper 4 bits, but in the lower 4-bit positions. So in this particular software, the way we go about that is we can swap the data in each block. And in this case, what we want to do is swap the nibbles inside the bytes. So we select that option, click OK, and what we've done now is we've swapped the upper and lower nibbles in each byte. We can now save this file as we did with the original file, because when we open this in the programmer, the upper 4 bits, which were the lower 4 bits, will be masked off. In other words, the file will then consist of only the upper 4 bits, but in the correct locations to be programmed into the prom. So if I save that, again we want the correct buffer n size so that we only say 512 bytes. We'll call this one upper. Save the file. So to use them, all we have to do is load each one in turn. So if we load the lower one, we'll now select the correct device. Okay, so we now have the PROM type selected. If we now look at the data that's going to be programmed, you'll see that the programmer has masked off the upper 4 bits, and it will just program the lower 4 bits into the PROM that we put into the programmer. We then select the other file, which is the upper bits, and then look at what we have. You'll see that we now have the upper 4 bits but in the correct positions to be programmed into the PROM, and then we can just program this into the PROM that's plugged into the programmer. We will then have 2 PROMs, one with the upper 4 bits and one with the lower 4 bits of each byte, which is what the MK14 requires. Okay, now that we have the PROMs, we can look at how to operate the MK14. I would say at this point there are different versions of the code available, so which one you use is up to you. It depends on what you intend to use the MK14 for. I've tried this particular board with all the different variants I could find, and it works fine with all of them. Okay, now of course the display on here is very small, so what I'm going to do is zoom in to the display so you can see what I'm actually typing in. Okay, so hopefully you'll be able to see this. It's quite a hard display to video because it's so small, but I'll go ahead and power up the MK14, and you can see it's come up in its reset state. It will go into this state whenever you power it up or press the reset key. The only difference is if you press the reset key, it does not erase the RAM. So if you've entered a program, you want to reset it, just press the reset key. You will only lose the data in the RAM if you explicitly overwrite it or if you power cycle the MK14. The display is split into 2 parts. The left hand 4 digits are the current address, and the 2 right hand digits are the data value at that address. So it's very easy to operate the machine. If you press the memory key, then you will see the current memory address that we're at and the data value at that address. If you want to change the address you're looking at, press the memory key and then press the or enter the address that you want to look at. In this case I've entered 0, and notice that we're now at address 0 and the value there is 08. If you press the memory key, then we will move on to the next memory location, so the memory address will increment by 1, and then the data value at that address will be shown in the right hand part of the display. And notice if I keep cycling through the memory, the value on the right as we go through the addresses is actually the first few bytes of the monitor program that we programmed into the PROMs. And that is because the PROMs are mapped to address 0 and up to address 511. So anytime you want to enter a program, you must enter it above that upper PROM address, otherwise you'll be trying to write into the PROMs, and of course that won't work. If you look at the manual for the MK14, it does give you the address space mapping, so you know where to enter the various parts of code to. If I press the 0 key, it takes us back to address 0. Now if you want to enter a program, what we have to do is select the address we want to start entering the program at. So in this case, if I enter 0F12, you'll see that the address is now showing 0F12, and the current data value there is E7. That's just the value that was there when we powered up the MK14. To enter a data value, what you have to do is press the term key. So I'll press the term key. Notice the display hasn't changed yet. After you've pressed the term key, enter the data value you want to store at this address. So if I enter 1, notice that we now have a 1 in the right hand part of the display, and then to save that in RAM you press the term key again. So I've now saved a value of 01 at address 0F12. If I press the memory key, it will increment the address, and we will now be looking at the current data value in that address. And again, it's the value that was there when we powered up the Mark 14. If I want to enter new data there, again I press the term key, enter my new data value, in this case I'll enter 2, and then press the term key again to save it. Press memory, takes us up to the next address, press term, I'll enter 3 this time, press term again, and that's all you do. You just select the memory address, press the term key, enter the value you want for data, and then press the term key again to save it. We can now go back to the start of our program. So if I enter 0F12, notice that what we're seeing in the data part of the display is a value of 01, which is what we entered. If I now press the mem key, we've gone to the next address space and we're looking at the value of 2 that I entered, 3, and that's how you would proceed. You just increment the memory each time and enter your new data. So the last thing in this video I'll do is enter the very simple test program that was in the user manual for the Mark 14. So we'll assume that we reset the Mark 14, so I'll press the reset key. Notice we're back in the reset state. Press memory, it's showing us the value at memory address 1. I want to enter 0F12 as my memory address, so we're now at the same address we were for the start of the last example that I gave. I want to enter a value of 90 at that address, which is a jump. So again, to enter data, press the term, then the value, then term again. We've stored that value of 90 at 0F12. Press the memory key, that will take us up to the next address. Press term, and then enter the new value that we want at that address, in this case FE, press term again, and that's it. All this will do is just loop round, jumping back to the start of the program that we've just entered. So to run the program, what we have to do is press abort, and it goes into a kind of a reset state. It's waiting for a program to start, and then we press go. It gives us the start of the address that it's going to run from. In this case we want to enter the start address of the program, so 0F12, and then we press term to enter that value. Notice the display has gone blank, it's not actually putting out any data, it's just continuously looping around between the two addresses. So a very simple test program, but the fact the display is blank means it's most likely working. I press the reset key, notice that we come out of that program, and then we can look back at the memory and we can see what we entered is a value of 90, and in the next address space is FE. So that's our program still there even though we pressed the reset key. So that's it for this video. I'll come back and do some more videos on what we can actually do with the Mark 14. It is quite a flexible machine considering how simple it is, and you can have a lot of fun with it. As I say, it's just a case of getting a hold of the parts you need to make it. Most are very straightforward, even the proms are fairly easy to get hold of, and it's just really a case of finding an old calculator with the right display type. And then you can build one and run the various programs that are available online or write your own.